Hi guys, so in the previous video we talked about the definition of the term isomerism and we also discussed chain isomerism in detail. So in this video we're going to be taking a look at positional isomerism, which like discussed previously is a part of structural isomerism. So the first thing that we're going to be doing is that we're going to be defining this term. So positional isomerism is exhibited by compounds that are in the same homologous series. This means that if one of the compounds is an alkane, the other one also has to be an alkane. If one of them is an alkene, the other one is also going to be an alkene, and so on. So both of them are in the same homologous series. And they need to have the same carbon skeleton, which means that the number of carbons in the longest chain needs to stay the same. Unlike the previous one, which was chain isomerism, in which the carbons had to be different. They also need to have the same molecular formula. However, the position of the functional group is going to be different. So this is the main part of this. So the first thing that we're going to be looking at is going to be alkenes. So in this case, we're going to number this alkene and then we're going to name it. So this is going to be but-1-ene or simply butene, because the position of the double bond is at the first carbon. Next, we're going to be taking a look at another isomer. In this one, the position of the double bond is in the second carbon. So because of that, it's going to be but-2-ene. So as you can see, the molecular formula is the same. However, when you name it, the name is going to be different. So because of that, these are isomers. And since the position of the functional group, which in this case is the double bond, is changing, they're going to be classified as positional isomers. Let's take a look at another alkene. If you name this, you're going to see that the double bond is in the first carbon, so this can be hexene. In this case, the double bond is in the second carbon, so it's going to be hex-2-ene. And if you number the last one, you're going to get hex-3-ene. So similarly, in this compound, the molecular formula stays the same. It's going to be C6H12. However, the name is going to be different. So now we're going to be taking a look at examples for alcohols and ketones. So for alcohols, we're going to be taking a look at the alcohol with the molecular formula C4H8O. In this case, we can have two positional isomers of the same alcohol. So if you number this alcohol, you're going to see that the OH group is attached on the first carbon. So this is going to be called propan-1-ol. Similarly, if you look at the next one and you number the carbons, you're going to see that the OH group is bonded to the second alcohol. So this is going to be propan-2-ol. As you can see, the names of these two compounds are different. However, the molecular formula is the same. So these are going to be classified as positional isomers. Similarly, let's look at ketones. So if we take a look at the molecular formula C6H12O, we can get these two isomers. So if you number the first one, you can see that the functional group is attached to the second carbon. So in this case, this is going to be classified as hex-2-one. Now if you look at the next one and you number the carbons over here, you're going to see that the functional group is attached to the third carbon. So this is going to be hex-3-one. So similarly, even though the naming is different, the molecular formula is the same. And the reason the naming is different is because you're changing the position of the functional group. So because of that, these are all going to be classified as positional isomers.